Welcome to the fifth lecture of this week. Today we will look into one specific case where we have B matrix equal to 0, that means the laminate is symmetric, and also the laminate is a cross ply laminate, that means the coupling between the shear and the normal and also the bending and twisting is not there. So, the problem is this, we have a laminate which is symmetric cross ply laminate. It is simply supported at all the edges and there is axial load applied, uniform axial load, and it is applied along both the directions. As well as there is shear. So, we denote the axial load as Kx multiplied by n bar, the shear as Ks multiplied by n bar, and the other axial load as Ky multiplied by n bar. Our axis is here x, y and z, and the dimension along x is a and dimension along y is b. And we have seen that for this kind of problems where B matrix is 0, we can separately solve the third equation, that means the equation that we got by setting out the coefficient of variation of AW equal to 0. So, that equation was this. So, this equal to 0 is our equation and this will help us find out n bar. Now, if I put the definition of this mx, my and ms in terms of the derivatives of w, I get this. We know that mx is minus dxx into del 2 w by del x2 minus dy xy into del 2 w by del x2 and dxx is absent here. So, we get this. Similarly, we get this and this equation, and mx is a negative of this quantity. So, that negative sign is put here. Now, our goal is to form algebraic equations from which we can find out n bar. So, we have to make assumptions for w now. Now, assumptions so, when we represented previously in this equation, the assumptions were w as a function of x y equal to I going from 1 to n, and then we have phi w I which is a function of x y into a w I, the unknown associated. Now, here what we will do is we will assume this as a double summation. So, instead of a single summation here, we will make a double summation in the form of double trigonometric series. So, our assumption would be this: m equal to 1 to capital M, n equal to 1 to capital N, x a function of only x. So, x m a function of only x multiplied by y n a function of only y, and then everything is multiplied with w m n. So, if I compare this with this, this n does not correspond to this end. Rather, if I see here that if I break the if I mean expand this, I get total m n number of terms, because the inner summation goes from 1 to m and the outer summation goes from 1 to n. So, we get total m n number of terms. So, n in the first equation here corresponds to m n in this equation, and similarly each combination of these x's and y's corresponds to a wi here. So, what we are doing here basically is there are m number of functions of x and n number of functions of y, and we are just making a combination of them, and we are each of them is a phi wi, and similarly Wmn is awi. So, here if I want to represent this as a single summation, then x m multiplied by y n can be written as, okay. So, generally what we do is we write the inner summation with n and outer with m, like what we did before. So, I would like to be consistent with that, although it hardly matters. So, n is equal to 1 to n and m equal to 1 to n. So, n is equal to 1 to m and m equal to 1 to m. So, x m n, the mnth term in this double series is can be written as, this is the phi I, and then we have there are the sum goes from 1 to n. So, it is m minus, okay. So, I can write just I here and we can write the expression for I, that will make it look clean. So, I equal to m minus 1 into n plus m. So, when so an mnth term can be represented, if I want to expand this and write as single series, then I is equal to this. Anyway, so we will just continue with this kind of approximation and develop the entire formulation from which n bar can be found out. Just one correction, this is not m, this is n, small n. Now, let us define the derivatives. So, we have del w by del x. I can write this as this double summation, n going from 1 to n, m going from 1 to m, and we can, if I differentiate this, this is a purely function of x and this is a purely function of y and this is constant. So, if I differentiate this, only this term would be differentiated. So, we have del x m by del x multiplied by y n of y into w m n. Similarly, if I want to take variation of it, then this cannot be varied, this cannot be varied, but w m n can be varied. Similarly, del w by del x del y with its variation can be written as n equal to 1 to n, m equal to 1 to m, and then x m cannot be differentiated because it is a function of only x. However, y n can be differentiated, I do not need to show this, and then we have variation of w m n. Now, before proceeding further, just to illustrate this summation, say if I equal to if m equal to 2 and n equal to 2, then w x y becomes x 1 y 1 w 1 1 plus x 1 y 2 w 1 2 plus x 2 y 1 w 2 1 plus x 2 y 2 w 2 2. So, we get 4 terms capital M multiplied by capital N. Now, I can define the double derivatives with variation. So, del 2 w by del x 2, I can write this as n going from 1 to capital N and m going from 1 to capital M, and then x m has to be differentiated twice, and we have y n and then variation of w m n. Likewise, we can write del 2 w by del y 2 is equal to n going from 1 to n, m going from 1 to m, x m multiplied by del 2 y n by del y 2 into variation of w m n, and then we have variation of del 2 w by del x del y, and we have n is equal to 1 to n, m equal to 1 to m, and then we have del x m by del x into del y n by del y into variation of w m n. Now, for this particular problem we have to make some approximation for x m and y n, and we know that our requirement is that we should at least satisfy the essential boundary condition. So, here at x equal to 0 a and y equal to 0 b, we have w equal to 0, and this is our essential boundary condition. So, this has to be at least satisfied. If we can satisfy the natural boundary condition, that is well and good, but at least this should be satisfied. So, for that we can write x m as sin m pi x by a, and we can write y n as sin n pi y by b. If I put this x m and y n here, we can see that that expression satisfies the essential boundary condition, and also for this problem it satisfies the natural boundary condition also. Now, depending on the support type, we could have chosen different approximations as well. Now, our job is to put everything in this expression. So, if I do it, the finally it looks like this. Here one thing to notice is, in these terms or in these terms, so wherever I have this i's here, and those came from because initially when we wrote the energy expression, I mean or the virtual work expression, we had these terms with suffix I that was multiplied with the variation of the unknowns. So, those terms here corresponds to this term, 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 and there I am writing this as w m n. So, the suffix I am using is m and n, whereas these terms which are inside these brackets, which came from the stress resultants mx, my and ms, and also these n also this from these terms which had j index. For that I am using the indices I and j to show the double summation. Again I could have used I and j for both or m and n for both, but just to show the difference we are using different terms. Now, we have already formed the equations. So, this delta w m n is not necessary here. So, these terms are not necessary because we have just already said that the coefficient of these terms is 0. So, this is not needed. Now, here if I look at this equation, this gives us total m n equations, m n equations, and then depending on the orthogonality these equations can be coupled or non coupled. So, here we have double trigonometric series. So, here what we get is an uncoupled system. So, for example, here what we have is sine into sine and that is multiplied with sine into sine. So, when I is equal to m and j is equal to n, I get non-zero value. If any of the pairs are different, then we get a 0 value, and same here also we get sine into cosine and sine into cosine. If I and m are same, j and n are same, we get non-zero value, but if any of the pairs are non-zero, if any of the pairs are different, we get a 0 value. So, for this set, this I mean with this assumption, we get a set of uncoupled mn number of equations. If they are if this orthogonality is not there, then we will get a set of coupled equations. So, we can write total n algebraic equations of this form f multiplied by w is equal to n bar multiplied by g into w, and they may or may not be coupled, may or may not be coupled depending on the approximation. On the approximation so, for the present approximation they are uncoupled. Are uncoupled. Now, what we will do is we will take some numerical values and look at it. So, this is eigenvalue problem. If I solve for this n bar, then we can get if I mean these eigenvalues would give us the values of n bar, and then these w's will give us the mode shapes. And just one thing, for present values also they are not everything is uncoupled, only f is uncoupled. F is uncoupled and G is coupled due to the presence of shear, G is coupled. So, okay. Now, let us look into the numerical values that will make it more easier to understand. So, let us say that we have a laminate with the lamination sequence 0, 90, 0, 0, 90, 0, and each layer is 0.2 millimeter thick, and then we have the material properties. The material properties Q is equal to 140.9, 30, 3, 10, 0, 006 GPa for each layer, and then we have say A equal to 1 and B equal to 1, and another information that I need is Kx is equal to 0.3, Ky equal to 0.3, Ks equal to 0.4. So, it has the presence of both Kx, Ky and Ks, and depending on that also your G can be coupled or may not be coupled. So, with that the F matrix that we get is this. We have 5, 92.3, 0, 0, 0, and then we have 0, 4 7 5 0, and then we have 0 0, again 0 0 4 7 5 0 0 and 0 0 0, and we have 9 4 7 6, and the G matrix that I get is 1.480400 minus 1.422, and then we have 0 3.7011, and then we have 1.422, and then we have 0 0 1.422 3.7011 0 minus 1.422 0 0, and then we have 5.9218. So, we can see that F matrix is a diagonal matrix. So, it does not involve coupling between different Mn terms, and G involves some coupling. So, when I said that F is uncoupled, that means it is a diagonal matrix. Now, if I solve the eigenvalue problems, we get the eigenvalues, that means the buckling loads and the corresponding buckling modes. So, the results that we get are let us say n bar. The first n bar that we get is 373.8 Newton per meter, and the corresponding eigenvector is 0.762400 minus 0.0558 minus 0.0558. So, this is eigenvector corresponding to the first eigenvalue. So, it signifies that the first term I multiply with the first approximation. So, 0.7624 into sin pi x by a into sin pi y by b plus 0, they do not matter. So, I mean, so they do not have any contributions, and then the last eigenvector is minus 0.558 into sin 2 pi x by a sin 2 pi y by b. Now, one thing I should have mentioned before, while solving this problem, the W has been approximated as summation n going from 1 to 2, m going from 1 to 2, and then sin m pi x by a sin n pi y by b W m n. That means, I have made a 4 term approximation. I could have made more or less term approximation also. Here for the demonstration purpose, I have 4 term approximation, and we have seen that if I just expand it, it is W11 sin pi x by a into sin pi y by b plus W12 into sin pi x by a into sin 2 pi y by b plus W21 into sin 2 pi x by a into sin pi y by b plus W22 into sin 2 pi x by a multiplied by sin 2 pi y by b. So, the eigenvectors that we get have 4 terms, and these 4 terms corresponds to this W11, W12, W21 and W22. So, for the first eigenvector I have only this and the last term present. So, I am multiplying with this and this, and this is the mode shape. The second eigenvalue that I get is 9 27.2 Newton per meter, and we have 0.3124, 0.3124, and then transpose. So, with this I get 0.3124 into sin pi x by a sin 2 pi y by b plus 0.3214 into sin 2 pi x by a multiplied by sin pi y by b. Now, one thing to note is that these eigenvectors, whatever the values we get, they are not the fixed values, they basically mean the ratio. So, for example, minus 0.7624 and plus 0.558 also resemble same eigenvector. If I multiply the eigenvector by any number, it is also the same mode. Now, many times that is why we represent these eigenmodes in a normalized form, but we are not doing it here. Third one, 2084 5 Newton per meter, and then we have here the eigen modes as 0.4684 minus 0.4684, 0, and then here we have 0.4684 multiplied by sin pi x by a into sin 2 pi y by b minus 0.4684 into sin pi x by a multiplied by sin 2 pi y by b. Last one is 226.5 Newton per meter, and here we have 0.5448, then 0, 0.4652, and if I write it in the function form, I have 0.5448 multiplied by sin pi x by a into sin pi y by b, because this is the first and we have last, plus 0.4652 into sin 2 pi x by a sin 2 pi y by b. So, these are the different buckling loads and buckling modes. Now, this gives us n bar. So, from this n bar I can find out the corresponding nx, I mean the corresponding compressive load and the shear load. So, n bar equal to 373.8. So, this gives us kx n bar, that is the compressive load along direction x, equal to 0.3 multiplied by 373.8. We have said that in this exercise we have considered kx equal to 0.3, ky equal to 0.3 and ks equal to 0.4, and then we have ky n bar equal to 0.3 multiplied by 373.8. Point 3 multiplied by 373.8, and then we have ks multiplied by n bar is equal to 0.4 multiplied by 373.8. All these are in Newton per meter, and similarly we can find the same thing for these buckling loads. So, here this tells us about the buckling loads, and from here we get the buckling modes. So, this completes the end of this brings us to the end of the discussion on buckling. From the next week we will start talking about vibration of composite laminated plates. Thank you.